Welcome to Lesson 15G, Rayleigh flow, compressible flow with heat transfer. In this lesson we introduce Rayleigh flow, which is flow in a duct with heat addition, but we neglect friction. We'll discuss it both qualitatively and quantitatively, and I'll do an example problem. This is a very abbreviated summary. I give a much more rigorous analysis in my compressible flow course. First, some approximations and assumptions. We assume the flow is steady, 1D. In other words, we ignore boundary layers and approximate the flow as uniform. V, however, is a function of x. It changes, increases or decreases, as you travel downstream. For example, V1 is shown here as smaller than V2. We always deal with ideal gases and constant area ducts. We don't allow for expansions or contractions in Rayleigh flow. This is an important approximation that all the gas properties, such as the ratio of specific heat, gas constant, etc., are constant. This is not strictly true, especially if there are chemical reactions or combustion, which can lead to different values of these constants. But this approximation enables us to solve these problems analytically. Finally, we neglect friction. There will be friction, of course, along the walls of the duct, but we'll deal with friction later in what we call thanoflow. Here are some practical applications of Rayleigh flow. When you have a gas flowing in a tube in a heat exchanger, and the tube is reasonably short with heat transfer, Rayleigh flow is a good approximation. We'll let Q dot be the rate of heat transfer coming into the gas from the outside. Same thing happens here, where the tubes are annular. A different gas or liquid outside of our tube provides the heat transfer into our tube, the middle one. Here's the same thing but with a transparent outer tube. We can also have a cross-flow heat exchanger, in which some outside fluid flows up in this case, while the flow through the tubes is in this horizontal direction. Again, if this flow coming up is hot, it transfers heat into our ducts. As you can see in all these cases, the tubes are short, otherwise friction would not be negligible along the wall. Here are some thermal images showing high temperature of the wall in an uninsulated portion of a duct. Another example is here. If some gas were flowing through this duct, the heat transfer would be the opposite way, from the gas to the surroundings. We can deal with either positive or negative Q dot in Rayleigh flow. Another example is the combustors in a jet engine or a gas turbine engine. Here the combustion chamber is a good candidate for the Rayleigh flow approximation. It's short, there's heat transfer to the gas, and at least this portion of it is constant diameter. Note that the heat doesn't always have to come from outside. Here it's coming from a flame, which changes the gas from air coming into some combustion products and air coming out. But in our simple analysis, we assume that all the flow properties are constant, as I mentioned previously. Here's a cutaway diagram of the combustion chamber in an actual engine. And here's what it looks like looking upstream at the flame. Afterburners are another example. In the downstream section of a jet engine, you can add fuel directly into the flow where it burns and produces hot exhaust gases that provide an enormous amount of thrust. This portion where we have a flame can also be approximated by Rayleigh flow. We'll start our analysis with a control volume. Here's our duct with flow from left to right, and we pick some control volume from location 1 along the inside of the duct to a downstream location 2. The gas properties at 1 are P1, T1, ρ1, V1, the speed, etc. Similarly at the outlet with subscripts 2 instead. Here you can see that the flow is accelerating. The acceleration is caused by heat transfer into the gas. As I mentioned, Q dot can be positive or negative. Most of our work will involve positive heat transfer into the gas. We'll also define A as the cross-sectional area of the duct. This duct can be round or rectangular, it doesn't matter. A is the cross-sectional area, which is constant, so we don't need a subscript 1 or 2. First, consider conservation of mass. Since the flow is steady, m.1 has to equal m.2, or ρ1, v1, a1, which we'll just call A, equal ρ2, v2, a2, or A. The A's cancel, so ρ1, v1 is equal to ρ2, v2. We'll call this equation 1. Now consider the linear momentum equation in the x direction. You should recall this equation from previous lessons. Here there's no gravity in the x direction. We're ignoring viscous forces. For our control volume, there's no struts or anything like that, but we do have pressure forces. On the left side of the control volume, we have P1A, and on the right side, we have P2A where P1 acts to the right and P2 acts to the left, hence the negative sign here. For a 1D approximation, beta is 1 at both the inlet and the outlet. The outlet, m dot, is rho 2 v2a, and at the inlet is rho 1 v1a, but there's another speed v2 and another speed v1 in this equation. So we write rho 2 v2 squared a minus rho 1 v1 squared a. Again, the a's cancel in each term, and our momentum equation ends up being P1 plus rho 1 v1 squared equal P2 plus rho 2 v2 squared. We'll call this equation 2. It looks somewhat like the Bernoulli equation, but it's not. This is valid for compressible flow in a duct. Equations 1 and 2 must be satisfied for Rayleigh flow, regardless of Q dot. So far we've dealt with conservation of mass and momentum, but we haven't said anything about heat transfer or the energy equation. It takes a little bit of algebra, which I won't show, but I'll summarize as we start with equations 1 and 2. We apply the ideal gas law. We also need the TDS equations from thermo and some other compressible flow equations from previous lessons. For example, T naught over T, the stagnation temperature over the static temperature, similarly P naught over P, etc. Combining all these equations and doing some algebra, we generate the Rayleigh curve, which some people call the Rayleigh line. I prefer curve since it's not a line, it's a curve. And this curve is on a TS diagram. I'll sketch it here. We plot temperature as a function of specific entropy, and we start with some known state, which we'll call 1. Suppose 1 is here. The Rayleigh curve that passes through 1 looks something like this. There are two branches. The upper one is the subsonic branch, and the lower one is the supersonic branch. Let's consider the case where Q dot is positive. Since there's no friction or other irreversibilities, this implies that specific entropy must always go up. It must increase. In other words, we can only move to the right on this diagram. As you add heat, in other words, we're moving down the pipe or the duct, adding heat along the way, we move along this Rayleigh curve. If we add more heat, we move further along until we reach some maximum temperature, and then the temperature decays slightly until we reach a point of maximum entropy. Again, starting with a subsonic Mach number increases continually along this curve, even in this portion, finally reaching sonic conditions at this maximum entropy point. Let's call this maximum entropy S star, which is the critical or the sonic state, since Mach number is 1 there. At this point, the flow is choked. You cannot keep increasing Mach number. If you tried, you would have to go along this curve in the negative S direction, which is impossible. You can't violate the second law of thermodynamics. Physically, what's happening is if you have flow in a duct starting at condition 1 and you keep adding heat, Mach number keeps increasing until it reaches sonic Mach number 1, and it can go no further. The same thing happens if the flow starts supersonically. In this case, since Mach number is greater than 1, the opposite thing happens. Mach number decreases as you move along the duct when heat is added, again reaching Mach number 1 eventually. You cannot continue backwards on this curve, so again the flow is choked. We conclude that Mach number approaches 1 in Rayleigh flow, regardless of which branch we're dealing with, subsonic or supersonic, when we add heat. Now let's consider conservation of energy. Without writing it all out, it reduces to Q dot equal m dot H2 plus V2 squared over 2, where H is the specific enthalpy, minus m dot H1 plus V1 squared over 2. We recognize this as H naught 2, the specific stagnation enthalpy, and this as H naught 1. Let's divide all the terms by m dot, giving us Q dot over m dot, which we'll call small q. And from our equation, we have H naught 2 minus H naught 1. But for an ideal gas, we approximate H as CPT. So we write this as Q equal CP T naught 2 minus T naught 1, since H naught is also CP T naught. This is our energy equation in Rayleigh flow, which we'll call equation 3. Looking again at our TS diagram and the Rayleigh curve, this critical point has a stagnation temperature of T naught 2 equal T naught star, where we use the star or the asterisk to indicate sonic or critical flow properties. Again, as we move along from some point 1 and add heat, we can finally reach sonic conditions. That turns out to be the maximum amount of heat transfer that you can add without changing the initial conditions. So at the critical values, Q equal Q max equals Cp T naught star minus T naught 1. This is the maximum heat transfer that we can add without changing the state 1, our initial point. What happens if we add more heat than that? Well, it would shift 1 to some other location and thereby create a whole new Rayleigh curve. But for this particular condition 1, the maximum heat transfer we can add is Q max, which is Q dot, the heat transfer, over M dot. I also want to mention the drop in temperature that I showed previously. Again, sketching our Rayleigh curve, and starting at state 1, adding heat, temperature keeps rising until it reaches some maximum value, and then it actually falls until we reach critical conditions. I like to call this the strange zone because temperature goes down as we add more heat, which is counterintuitive. Dude, are you telling us that you add heat but the temperature goes down? That just don't make no sense. Well, it's true. You'll have to take my compressible flow course to learn why. Okay, man. I will. There's a lot of algebra involved in analyzing these problems. I'm not going to show all that here. Instead, I'll give a summary of the equations for Rayleigh flow. You recognize our mass, momentum, and energy equations here and our maximum heat transfer. We can also get these other property ratios, both for static properties and stagnation properties. To solve Rayleigh flow problems, I give you a step-by-step procedure here. Again, we have to start with known conditions at state 1 and a known rate of heat transfer Q dot. We use our energy equation to calculate T naught 2. We would have to know all of these things except T naught 2 here. Step 2 is to calculate T naught 1 over T naught star from this ratio equation, and then calculate T naught 2 over T naught star by using ratios as shown here. Step 4 is to use this equation to calculate Mach number 2. This is the hardest step because this is an implicit equation, and you usually have to use some iterative method to solve for it. I typically use the false position method, which you can learn about in one of my other videos. Finally, we use the other equations, the ideal gas law, plus speed of sound equation, etc., to get any other desired property at state 2. Let's do an example to illustrate this. Here's our duct with heat added. I show a flame here, which is the source of our heat, but we could easily have heat coming in external to the duct. In this case, we have air and fuel entering this round tube at specified conditions and speed. These are all at location 1. I tell you how much heat transfer is supplied or added to the gas. And we have to estimate the temperature, pressure, velocity, and Mach number at location 2, downstream of where this heat transfer has been added. Our assumptions and approximations are the same as what we said at the beginning of this video, and I apply the equations and numerical values here. We use the ideal gas law, and when we plug in our values, we get this density at 1. We use our equation for speed of sound to get C1, and then since we know V1 and C1, we get our Mach number MA1. We can also get T naught 1, the stagnation temperature, which is 1 plus K minus 1 over 2, where I'm using the K for air here. Plug in our Mach number and T1, which was given, and I get T naught at location 1. I'm keeping about 5 significant digits here to avoid round-off error. All final answers will be given to 3 digits. Now let's do our step-by-step process. First we calculate M dot 1, which is the same as M dot everywhere. We just calculated rho 1. We know the speed and we know the area, so we get M dot. Little q is Q dot over M dot. Q dot was given and we just calculated M dot. We need a unity conversion factor here. A kilojoule per second is a kilowatt, so the kilowatts and the seconds cancel, leaving us with 1050.0 kilojoule per kilogram as our little q. Finally, T naught 2 is T naught 1, which we have from up here, plus our little q, and for air we know Cp, and we get 1598.5 K Kelvin as our value of T naught 2. In step 2, we'll calculate the sonic or critical reference values. First we calculate T naught 1 over T naught star with this equation. This turns out to be 0.12914, from which, since T naught 1 is known, T naught star is 4283.7 K. Step 3 is to apply these ratios to get T naught 2 over T naught star. T T02 was 1598.5 K, and we know T01, and this ratio is the same as this, giving us this final answer, which we plug into here in step 4 and solve implicitly for Mach number. Again, I used the false position method and got Mach number 2 as 0.31429. Note that it's still subsonic, as it must be, since Mach number 2 approaches 1 as we keep adding heat. It can never become supersonic. The highest Mach number 2 we can get is 1. Finally, we calculate other desired properties. First, I want to do another sanity check or verification. Namely, let's make sure that Q dot is less than Q dot max. Since this flow is not choked, we know that because it's still subsonic. Well, Q dot max is m dot Cp, T naught star minus T naught 1. When we plug in all the numbers, we have m dot times Cp, T naught star minus T naught 1, and then our unity conversion factor, the reciprocal of the one we used before, and we get that Q dot max is 16109 kilowatt. This is greater than our actual Q dot, which was 4514 kilowatt. So this step is verified. We can calculate all the desired properties at state 2. I won't show all of them, but for example, T2, how do we get it? Well, there are various ways, but let's take T naught 2 over T naught star, which is known from our previous calculations, and we calculated Mach number 2. So from this, T naught 2 is this ratio value times T naught star, giving us T naught 2. But we want static temperature T2. Well, for that, we can use our old friend T naught 2 over T2. Solve this for T2. I get 1567.6 K. Similarly, we can calculate other properties at 2. I'll summarize all my final answers to 3 digits. T2 is 1570 K. P2 is 439 kPa, V2 is 249 meters per second, and Mach number 2 is 0.314. Finally, recall that V1 was 80 meters per second, so we've greatly accelerated the flow. Mach number also went up from about 0.17 to 0.314. Temperature went up, pressure went down. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.